So imagine you drew a beautiful lifelike picture of a horse. Look at that. Look at how lifelike that is. It's almost like a picture, how close that drawing is to a horse. And you're really excited about it. And so you bring it in, you show everybody. But everybody can't really see. It's a little too small. But luckily you got a buddy who's got your back. Check it. And your buddy brings a blown up version of that picture. Notice how similar it is to the previous version. Just like the previous picture, it is a lifelike picture of a horse. And he replicates your dimensions and your art perfectly. And so now more people can see it. A bigger crowd forms, right? But you want to show everybody, and your other friends got your back. Check it. And your third friend brings an even bigger version of your painting. Notice how the shape of the painting is very much the same. Now more people than ever can see your beautiful, beautiful work, and it's a blown up version, right? That's all that is. It's just a bigger version of the previous one. For example, if you have a buddy. For example, if you resize it improperly, it's no longer the same lifelike picture of a horse, right? It looks more like a donkey or giraffe now, right? And so it's obvious that this is wider than it is, or this is longer than it is wide. And in this one, it seems almost like a square, right? It's not properly blown up, and so the picture gets distorted. So this is how ratios can be utilized in geometry. When you have similar shapes, they belong to a scale that helps us figure out how big they need to be. And in relation to each other, we can find the missing sides sometimes. So how do we know if it's a bigger version of the original or if it's a distortion? Well, we have to use something called scale in the utilization of figuring out similar shapes. Yeah? Awesome. Okay, cool. So let's keep moving. So imagine now, rather than just a picture, that we're going to get rid of the picture and we're just going to keep the boxes, right? So this is what it would look like as a geometry problem, right? You would be given shapes and you'd have to figure out if they're similar. Now, a way you can figure out if a shape is similar or not, you can check the angles. Since these are all rectangles, we're good to go. And then you can check out how the sides relate to each other. So 5 times what turns into 10? 5 times 2. So that is going to be our first scale. 5 times 2 gets to 10, and it works for both dimensions because 2 times 2 equals 4. And so if we multiply each side by 2, we're going to get a similar shape that is of a bigger scale, right? And how this goes to this goes to the next one. 10 going into 30, you need to multiply it by 3 to get to 30. 4, multiply it by 3 to get into 12, right? And so here are some of the dimensions just written out, just if you work better in that way. Notice from here to here is times 2, from here to here is times 3, and it's the same, right? So, cool. So let's see how you might see this presented in a geometry problem. So here we have some blanks missing, and let's just say that the prompt lets us know that we are dealing with 3 similar shapes. Okay, so we know that 5 times 2 gets us to 10, therefore 2 times 2 will get us to 4, right? And to represent this numerically, 5 times 2 gets us to 10, 2 times 2 will get us to 4. And we can do the same thing here. We're not given this, so we can't assume, but 4 times 3 gets us to 12. And so this 10 times 3 will get us to 30, okay? So it's not always going up, always. Sometimes you need to go down. So in this instance, we're given the fact that both of these shapes are similar. Cool. So how do we figure out what this remaining side is? Well, we know that 5 times 6 gets us to 30, but we don't have this number. So rather than using multiplication, in this instance, we need to use division, right? So 30 divided by what gets us to 5? 30 divided by 6 gets us to 5. 30 divided by 6, 5. So we need to do the same thing over here. 12 divided by 6. And what that gets us is 2, right? So that's our answer there. So keep in mind, that's how this works as far as you either multiply to go up or you divide to go down. Something to note, scale works for the sides, right? It doesn't necessarily work for area. Right on. Now you know how scale works, similar shapes work. Here are 3 example problems that you can try to test your skills. In the, I guess I'll put the answers somewhere. I don't know, probably in the description somewhere. So if you need help, you can always ask a question down below in the comments. Otherwise, good luck with your similar shapes and your scale work. And yeah.